This video is about doing problems 1 through 5 on the electric potential sheet. If you were able to do it with just looking at the solution, there's no need to look at this. So feel free to stop watching. Otherwise, stick around. Here we go. Number 1. So just so that we can all see the sheet I'm working with, it's that one there. Between 2 points in space, there exists a 15-volt potential difference, right? So the voltage is 15 volts. Now, I don't know which point is at a higher potential or a lower potential. That's not really what the point of this problem is. How much work does it take to move a 4 coulomb charge through this potential difference? So Q naught is 4 coulombs. Therefore, and it's a positive 4 coulombs, but not that it matters because we're just going to go work is equal to Q naught delta V. We are not dealing with the signs of anything, right? So let's just figure out how much work. So that's 4 coulombs times 15 volts. And remember, a volt is a joule per coulomb, so that is 60 joules of work. Now, if I'm pushing that charge through that potential difference to a place it doesn't want to be, like against the electric force, that work would go into increasing potential energy. If, for example, I put that charge in, it naturally goes through that 15, that could be the change in the kinetic energy, right? Remember, work is just a shorthand for the change in energy. 2. It requires, the part B of this. We didn't do the part B of this. Let's do the part B. 1B. An electron through a potential difference. Okay, so an electron we know has a Q naught of negative 1.6 times 10 to the negative 19th coulombs. We're asked to find this in both joules and electron volts, right? So if I want to find this in joules, I'm going to plug in my charge in coulombs. This is 1.6 times 10 to the negative 19th coulombs times 15 volts. And that I gotta put in a calculator. I think I know what the answer is, but I don't want to be wrong. Okay, yeah, 2.4 times 10 to the negative 18th joules. Now if I redo that, but when in electron volts, the easiest thing rather than just doing a conversion, is to convert my charge into elementary charges. So this would be in terms of elementary charges, 1 elementary charge through a 15 volt potential difference to give me 15 EVs. All right, nice and simple. 2, it requires 100 electron volts. So that's the work that's required to move a charged object through a potential difference of 25 volts, right? So the delta V is 25 volts. What's the charge in the object in coulombs? Well, if it's in coulombs, I probably just want to convert this to joules because that's going to be the most convenient thing then. And so this is 1.6 times 10 to the negative 17th joules. So what did I do there? I did a 2 shorthand here. 100 electron volts times 1.6 times 10 to the negative 19th joules per electron volt and got that number. You can see that conversion on the front of your table if you forget it. And then I can just use my work is equal to charge times potential difference. And I get the 1.6 times 10 to the negative 17th joules is equal to Q naught times 25 volts. And so then if I do that, Q naught is equal to, excuse me, 6 exponent 17 divided by 25 equals, and that's 6.4 times 10 to the negative 19th coulombs. Now, how else could I have done that? If I didn't want to convert, first I could have done this by plugging in 100 electron volts is equal to Q naught times 25 volts. And then when I divide that across, Q then has to be 4E. And then if it's 4E, that's 4 times 1.6 times 10 to the negative 19 coulombs. And then you get the same answer. You can decide what you think is easier. Notice here, all of these problems are just about knowing and understanding the units. 3. When moving a 3 microcoulomb charge, so Q naught is 3 microcoulombs. I'm going to automatically convert that. Between 2 points in space, 6 joules of work is done. So 6 joules of work is done. What's the potential difference between these 2 points? Delta V is equal to the work done per charge. So very simply, 6 joules over 3 times 10 to the negative 6 coulombs. The potential difference is going to be 2 times 10 to the 6th volts. All right, 4. How much electric potential energy? Oh, now this is different. This is not about potential difference. Does a 20 microcoulomb charge have at a location where the electric potential is 300 volts? Okay, so notice here, I'm looking for EPE because we're talking about what's happening at one point in space, whereas 1, 2, and 3 were about moving the object through 2 different points in space. So that's the difference in the text here. So this is 20 times 10 to the negative 6. So I use that electric potential is the electrical potential energy per unit charge at that location. And so I can plug in then 300 volts is equal to EPE over 20 times 10 to the negative 6 coulombs. The electric potential energy of that amount of charge at that location in space then is 6 times 10 to the negative 3rd joules, or just 0.006 joules. All right, 5. An object with a charge of 30e, so plus 30e, and a mass of 4.5 times 10 to the negative 25 kilograms is placed in an electric field at rest. It speeds up as it moves through a potential difference of 500 volts. How much work was done to the object in electron volts, in joules, and final speed? Okay, so here we go. A, work equals Q naught delta V. Once again, we're not dealing with signs because the sign conventions get really freaky here. So let's just do this in electron volts. So I'm going to put in my charge in, my charge in elementary charges. Wow, that just... So what is that? That's 15,000 EV. All right, cool. Then B, what is that in joules? Well, we can just do the conversion, or I could plug that in, convert to coulombs. I'll just do the conversion this time. Times 1.6 times 10 to the negative 19th joules per electron volt. And that gives me, I don't know off the top of my head, 15,000 times 1.6 exponent negative 19. 2.5 times 10 to the negative 15th joules. All right, so now here we go. C, what's the final speed? Well, here we have to use the notion that work is equal to the change in the kinetic energy. And so I know what my work is. So that's 1/2 mv final squared minus 1/2 mv initial squared. We're told that it starts at rest. And notice here, that's why I really like my notation of v with the little strange wings on it, because I've got 2 different v's in the same problem. So that goes away. So now the question is, do I use electron volts or do I use joules? What do you think? Hopefully you're saying joules, because this thing has kilograms and meters and seconds, and we know that joule is a kilogram meter squared over second squared. Electron volt doesn't break down in the same way, so anytime I'm trying to relate energies to our macroscopic type quantities here, the units have got to work out, and therefore I've got to be using the work in joules. So electron volts is an easier way for comparison of things, but it might not be better for a given problem. So negative 25 kilograms V final squared. All right, and then we can throw this into our calculators. Okay, square root of quantity, and then we get that final speed is plus or minus, get rid of that because I just want the speed, 10,000, 130. So I got to do the scientific notation. Looks like 1.03 times 10 to the 5th meters per second. And just so you know, particles, really small particles, when they're subjected to electric fields, generally end up going really, really fast. So that number makes a lot of sense to me in terms of its scale. So there you go. Hopefully what you got from this is that your choice of units is super important. We can't mix and match. As you go onwards for 6, 7, 8, 9, and 10, you'll be using a lot of these, as well as our notion that the electric field intensity E is equal to the potential gradient, delta V over delta S.